The Sun rotates on its axis once in about 27 days. This rotation was first detected by observing the motion of sunspots. The Sun's rotation axis is tilted by about 7.25 degrees from the axis of the Earth's orbit, so we see more of the Sun's North Pole in September of each year and more of its South Pole in March. The Sun spins on its axis, but it is a ball of gas or plasma. It does not have to rotate rigidly like the solid planets and moons do. The different latitudes of the Sun spin at different rates. In fact, the Sun's equatorial regions rotate faster, taking only about 24 days, than the polar regions, which rotate once in more than 30 days. Because of the different rotations, it distorts the magnetic field, which bursts out to form sunspots. A reversal of magnetic poles occurs every 11 years, and the number of sunspots also reaches a maximum every 11 years. The complete cycle of solar activity is 22 years. Solar flares are a sudden explosion of energy caused by tangling, crossing, or reorganizing of magnetic field lines near sunspots. It is a sudden flash of increased brightness on the Sun. The surface of the Sun is a very busy place. It has electrically charged gases that generate areas of powerful magnetic forces. These areas are called magnetic fields. Powerful flares are often, but not always, accompanied by a coronal mass ejection. Even the most powerful flares are barely detectable in the total solar irradiance. The last solar flare to hit Earth was the solar storm of 1859, also known as the Carrington event, and it was a powerful geomagnetic storm during solar cycle 10, during 1855 to 1867. A solar storm of this magnitude occurring today would cause widespread electrical disruptions, blackouts, and damage to extended outages of the electrical grid. The solar storm of 2012 was of similar magnitude, but it passed Earth's orbit without striking the planet, missing by 9 days. The next layer after the photosphere is the chromosphere. The chromosphere literally means the sphere of color, and is the second of the three main layers in the Sun's atmosphere, and is roughly 3,000 to 5,000 kilometers deep. Its shell is 10,000 kilometers thick, and due to its low density, is relatively transparent, resulting in the photosphere being regarded as the visual surface of the Sun. It's seen during an eclipse as a pinkish glow surrounding the Sun, and the pink color comes from the emission of light from hydrogen atoms. The chromosphere is hotter than the photosphere, with temperatures in the chromosphere ranging from around 6,000 to 2,000 degrees Celsius. Chromospheres have been observed also in stars other than the Sun. The Sun's chromosphere has been hard to examine and decipher, although the observations continue with the help of the electromagnetic spectrum. The Sun's corona is the outermost part of the Sun's atmosphere. Streamers and filaments of outward-moving, high-temperature plasma curved by the Sun's magnetic field. The Sun's magnetic fields affect charged particles in the corona to form beautiful features. These include streamers, loops, and plumes. We can view these features in detail with special telescopes. It extends out several million kilometers, and the temperature of the corona is extremely hot, at 1 million Kelvin. This is where most of the Sun's X-rays are made. It's not very dense, so it's not as bright as the Sun's surface. The corona is usually hidden by the bright light of the Sun's surface, and that makes it difficult to see without using special instruments. However, the corona can be viewed during a total solar eclipse. High-speed protons and electrons are cast outward, making solar wind, which powers the aurora on Earth and produces the tails of comets. In essence, the Sun is a perfectly normal example of the G-type main sequence star. And like all stars, it has a lifespan characterized by a formation, main sequence, and eventual death. This lifespan began roughly 4.6 billion years ago and will continue for about another 4.5 to 5.5 billion years, when it will deplete its supply of hydrogen, helium, and collapse into a white dwarf. To break it down, the Sun is about halfway through the most stable part of its life and is still relatively young. Over the course of the past 4 billion years, during which time planet Earth and the entire solar system was born, it has remained unchanged. This will stay the same for another 4 billion years, at which point it will have exhausted its supply of hydrogen fuel. When that happens, some pretty drastic things will take place. The sun, like most stars in the universe, is on the main sequence stage of its life, during which nuclear fusion reactions in its core fuse hydrogen into helium. Every second, 600 million tons of matter are converted into neutrinos, solar radiation, and roughly 4 times 10 to the 27 watts of energy. For the sun, this process began 4.57 billion years ago and has been generating energy this way ever since. However, this process cannot last forever since there is a finite amount of hydrogen in the core of the sun. So far, the sun has converted an estimated 100 times the mass of the Earth into helium and solar energy. As more hydrogen is converted into helium, the core continues to shrink, allowing the outer layers of the sun to move closer to the center and experience a stronger gravitational force. This places more pressure on the core, which is resisted by a resulting increase in the rate at which fusion occurs. Basically, this means that as the sun continues to expand hydrogen in its core, the fusion process speeds up and the output of the sun increases. At present, this is leading to a 1% increase in luminosity every 100 million years, and a 30% increase over the course of the last 4.5 billion years. In 1.1 billion years from now, the sun will be 10% brighter than it is today, and that increase in luminosity will also mean an increase in heat energy, which Earth's atmosphere will absorb. This will trigger a moist greenhouse effect here on Earth that is similar to the runaway warming that turned Venus into the hellish environment we see there today. In 3.5 billion years from now, the sun will be 40% brighter than it is now. This increase will cause the oceans to boil, the ice caps to permanently melt, and all water vapor in the atmosphere to be lost to space. Under these conditions, life as we know it will be unable to survive anywhere on the surface. In short, planet Earth will come to be another hot, dry Venus. All things must end, and that is true for the sun. It's not going to happen anytime soon, but one day in the distant future, the sun will run out of hydrogen fuel and slowly slouch towards death. This will begin in approximately 5.4 billion years, at which point the sun will exit the main sequence of its lifespan. With its hydrogen exhausted in the core, the inner helium ash that has built up there will become unstable and collapse under its own weight. This will cause the core to heat up and get denser, causing the sun to grow in size and enter the red giant phase of its evolution. It is calculated that an expanded sun will grow large enough to encompass the orbit of Mercury, Venus, and maybe even Earth. Even if the Earth survives, the intense heat from the red sun will scorch our planet and make it completely impossible for life to survive. To show the sun's rotation, I'm going to take a large bowl and fill it with water. After filling it with water, place some drops of coloring of some kind, like food dye, chocolate syrup, or soy sauce. I'm going to put some blue food coloring inside the bowl and then spin the bowl to show what happens when liquids rotate. After rotating it, you can see that they all move at different rates and speeds.